Thank you.
So this is V1. V1 is 1 over root 2, 1 over root 2, 0. The vector
0.
V2 is 1 over root 18, negative 1 over root 18, 4 over root 18. And then V3 is 2/3, negative 2/3,
Negative 2/3,
negative 1/3. So we want to find U1, and you can see we have the formula. It's 1 over sigma A multiplied by V1. Okay, so it's going to be 1 over 5. I think they should have said sigma I maybe, but we are going to see about that. So the you can see we have a first value there and another one, right? So we are going to do 1 over 5, and then matrix A. Matrix A is given there. Let me write it. A equals 3, 2, 2, 2, 3, negative 2. Okay. So this is going to be 1 over 5. And then you have 3, 2, 2, 2, 3, negative 2. And then you take V1, which is 1 over square root 2, 1 over square root 2, 0. Right? So this is going to be, if you multiply them out, 3 over root 2 plus 2 over root 2 is 5 over square root of 2. You still have 1 over 5 outside there, right? And then you do 2 multiplied by 1 over root 2 plus 3 multiplied by 1 over root 2 is 5 over square root of 2.
It's also 5.
And then if you multiply this vector by the scalar out there, you get 1 over square root of 2, 1 over square root of 2, and this becomes your U1, right? And you can see, you see the matrix U, we got that for U1. And this one is the U2, right? Yeah. Yeah. So let's find U2. I hope you have written this.
Now let me, I'll try to do it by myself. 1 over 3.
Yeah.
2, 3, 2, 2, 3, negative 2 times second 1 over 18, 1 negative 1 over 18, 4 over square root 18. And we have 3 minus 2, it's 1, and plus 8, 9 over root 18, second 2 minus 3, negative 1, minus 9 over root 18 times 1 over 3, it will be 3 over root 18 and negative 3 over root 18, right? No, we can change it. I mean, like, simplify. It will be 1 over root 2. And yes, negative 1 over root 2.
So your U2 is 1 over root 2, negative 1 over root 2. So looking at this formula, I think it's better to write 1 over sigma I, because the sigmas are going to
Okay,
change.
I agree with you. Sigma I.
Yeah.
Okay, I agree.
So that's how we come up
So,
with the
okay,
U,
now I understand.
with the U matrix in SVD. Yeah.
Okay, SVD understandable. Okay. If you can, could you also send me some, and also could you send this file which you're showing me, this one?
You have it.
Oh, I have it. Oh, sorry.
Yeah. Let me.
Sorry.
So I just went back to
My mistake.
to the messages,
No
and
worries.
then I
find
clicked
it.
on
I will
that.
find.
Yeah, it's on Friday,
Okay.
22nd October. Yeah.
Okay. Okay. Okay, I'll check it out. So move on. Lecture 8B, where we started about complex analysis. Here's everything is getting, actually everything is understandable when we're talking that. Let's try from them. Where I don't see. Could you explain me the difference between, so we studied complex analysis, we studied continuity, derivative, so or it's better to move to the homework. What do you say? I have a lot of questions here, actually. Okay, let's move to fresh homeworks. Let's start from the beginning.
You're talking about my homeworks, right?
Yes, homeworks which you provide me.
Okay.
Let's start from the day before yesterday, where we talked about differentiation of complex valued functions. There were homework. Okay, first one, we understand how to do it, -2i, where we used earlier formula. Second, it's equals 1/3. Third equals 6i. If you allow me, I can. Oh yeah, you open it. Go.
This is the one.
Go up. Is it continuity?
Yeah, this one is for continuity.
Okay, yeah, let's start from here. So my answer was that it's not continuous. First of all, I tried to find limit when z approach -i. It equals 1/-2i. Yeah, and also sorry about that.
It's okay.
Oh, I thought I turned off the sound. So that was my mistake. After that, I tried to find f of I, function of I, which is not exist because it's divided to 0. So after that, we can say that the function not continuous, right?
Yep.
Okay, B. I also here I tried to find a limit, which is 1/6 + 2i, and I tried function of I, which is also 1/6 + 2i, which are equal to the limit, and we can say that the function this function f of z continues at point z equals 1 plus 2i.
Yeah, that's right.
Okay. C, just clarifying, did I everything correctly? F of z here in this question C, I found limit which is equals z over 1 over 2i, and function of 0 is also 1 over 2i. It means that this function is continuous at point z equals 0. D. I found limit which 1 over negative 2 plus 3i, and the function of this point is the same, they're equals. So the function is continuous at point z equals negative 2 plus 3i.
Yeah.
So move on.
We move on to the next homework.
Yes. Complex derivativity. No, it was. Scroll up. Yeah. Oh, no. Yeah. Here, more examples, homework. Whereas z function of z equals 3z squared minus z plus 4. Here was a problem, a little bit I confused, because we talked about the formula which we use to find complex differentiation. When we say that the z plus delta z minus z divided to delta z, right?
Yeah.
In this case, do I need to add delta z to each z?
You don't need to use that formula.
I don't need to use that formula?
No.
Okay.
Because it's going to be so long. And that is why I gave you more rules. This is one formula. This is one formula for finding derivatives. And it's the most basic formula because it's the definition of a derivative, and that's why we call it a first principle. But now the same formula gives birth. It gives birth to these other formulas. The power rule, product rule, quotient rule, all these are children to that formula, and they are much easier to use.
Okay, never mind. I'll do it again by myself because
so
it says yes, differentiation rules.
So here use the power rule. I wanted to use the power rule there, and then you can try using the either the quotient rule or the product rule for the second problem.
Okay.
And it's going to work for you.
But I use this formula. Okay, I will. On the way. So let's move on to the analyticity. I guess it was analyticity, right?
Yeah.
Analyticity. Let's start from the first assignment. Could you scroll down a little bit? Where is our homework? Yeah, it's right here. Oh yeah, it's here. Here's the question: that the analyticity is the same, the complex differentiation, right?
Yeah.
I remember that they confused too, and I need to use these rules, differentiation rules, to solve analyticity problem, right?
Remember we talked about analyticity again, right?
And
then we came up with only one condition necessary for a function to be analytic. The Cauchy-Riemann condition.
Cauchy-Riemann condition. Do I need to use Cauchy-Riemann condition here?
Yeah, you can just use Cauchy-Riemann conditions there. But as for this homework, you just needed to find, here you just need to use Cauchy-Riemann conditions, or you could use the limit definition of a derivative.
So for the first task, it was difficult to me to use the same method that we use for complex differentiation, but
Yeah.
I can use this for rules for formula, which you recommend me to use for first for the previous homework. Let me open it here. So okay, I still a little bit confused. I think we need to, maybe it's better to restart it, because I can use differentiation rules to find complex differentiation, right? But also I can use this first principle of complex differentiation to find itself. I mean the formula when we're talking about the z plus delta z minus f of z divided to delta z. Okay, let's move to analyticity. Oh no, it's an analytic function.
So for example, did you attempt this one?
No, it was difficult for me because it's have top and bottom, and I didn't understand how. I tried to do second one. We can check the second one, but for the second one, I used the first principle method, and the answer was like just. And again, my question is, do I need to? But I didn't use this rules, differentiation rules formula. Do you see what I mean? I used just, and it was too long equation, too long solution.
So this is what you should have done. Realize that this is not a function of z. You have a variable x and you have a variable y. Right? You should have tried to bring back the z into your
Can we
equation.
do this test together, please?
Yeah, let's try this. So realize the top part is x minus iy minus 1, right? I just rearranged.
Yes.
And then the bottom part is x squared minus 2x.
Yes, plus 1.
Minus 2x plus 1. And then we have plus y squared, right? So when you look at that first function, x minus iy, you realize that that is going to be the complex conjugate z bar, right?
Yes.
It's going to be the complex conjugate z bar. Just 1 sec, let me get to that question on my book.
Yeah, sure.
So it's f of z is x minus that. I was picking the questions at random. So I'm just looking for it. Somewhere here. So this is, so we did that. We checked, this one we checked for z bar, right?
Yes.
And
yes.
That was the talk of analyticity. I can see it there, second case. So I've seen that one. Oh yeah, I found it. Okay, so realize that the top part, you see this top part?
Yes, I see.
It's Z bar, you agree?
I agree, yes, Z bar.
It's the complex conjugate, Z bar. And then the bottom part, so this is going to be Z minus 1 bar. So X minus 1 squared plus Y squared. So let me write this one the way it is without expanding. So this is X minus 1 squared plus Y squared. So we have Z plus Z bar over 2 minus Y minus I. I'm the one who did it. I have my solution, but I see. I see what just happened. So realize Z is always equal to X plus IY, right?
Oh, I got it. What are you talking about?
And then Z bar, you get what I'm trying to do?
Yes, I see. I know. Yes.
If you add them up, you're going to get 2Z
yes,
plus Z bar equals 2X. So what does it mean? It means that X equals Z plus Z bar divided by 2. And then if you subtract them up, you're going to do Z minus Z bar equals IY minus negative IY. That's going to be
0.
2IY.
2. Oh, yes.
And so IY is going to be equal to Z minus Z bar divided by 2. Right? And then Y is going to be equal to Z minus Z bar divided by 2I. So you have to replace the X and the Y with the Z and the Z bar to make it a function of Z. So it's going to be F of Z equals, we just saw that X is going to be Z plus Z bar over 2, right?
Yes.
So this is going to be Z plus Z bar over 2. And then you have minus 1. And then IY is Z minus Z bar over 2.
Negative minus.
So it's going to be
Z
minus
Z
plus Z bar over 2.
Why?
It's Z minus Z bar over 2. So minus is plus. Right? And then we can.
But you have also minus in front.
Yeah. Okay. Let me write it properly for you to see. So this is minus. If I put a bracket, I'm going to have Z minus Z bar divided by 2. But if I don't have a bracket, the minus inside is going to become a plus. Yeah, that's what I was saying. So so if I remove the bracket, this is going to become a plus like that.
Okay.
So,
okay.
and then at the bottom, so let's deal with the top first. So z plus z bar over 2 minus z plus z bar over 2, they cancel out. At the top, we only remain with -1.
Okay.
Right?
Yes.
Now let's go to the bottom. We
But
replace
z bar is the same, no?
what?
I mean, like we have two z bars.
At the top?
Yes. Z is canceling out, but z bar, it's positive. Two z bars.
Oh, yeah. Yeah. So it's going to be 2 z bars.
Or z bar negative -1.
-1.
Over 2. Over 2. Over 2 also. 2 z bars over 2.
So it's going to be z bar -1.
Yeah, z bar -1. That's.
Yep. Z bar -1.
Okay.
Okay, then we go to the bottom. We replace x with z plus z bar over 2 -1, and then we are squaring that. So it's going to be z plus z bar over 2 -1, and then everything is squared. And then we got plus y
z
squared.
We can say
No, plus.
Yes, z minus z bar over 2i.
Z minus z bar over 2i squared, like that.
Oh, okay, yes.
So let's try to make this simple. This is going to be z plus z bar
-2.
-2.
Oh, -2.
Over 2.
Divided to over 2.
Squared, right?
Yes.
And then this is going to be plus z minus z bar squared. That's 2 minus z bar squared. And then 2i at the bottom. It's going to become -4.
Oh, -4, yes. And 4 here.
So if we try to open these up, you know, I could switch this to 4 as well.
Yes.
Right? This could be 4, and then the bracket is just up there. And then I could pull this minus sign up.
Like I agree.
And then we subtract. And this is z minus z bar. It's going to be quite a long expansion. So let's do it. So let's keep this as it is. And then we treat this as a unit. You see this one? So it's going to be z plus z bar squared, right? Minus 4 z plus z bar plus 4, right? And then minus z minus z bar squared.
Which is cancel out.
No, they don't, because one of them is minus, the other one is plus. I also thought they would.
And we have z plus z, z negative z minus z bar.
Yeah.
Plus 1.
Where did you get that?
Oh no, they're not cancel out. Sorry.
Yeah, so you need to open this. This is going to be z squared plus 2 z bar plus z bar squared.
Z bar squared.
And then the other one is going to be minus z squared minus 2
plus
z.
Oh yeah, minus.
Z bar. Let me change the pen. So minus 2 z bar plus
z bar squared.
Z bar squared. So if you subtract the z squared cancels with the z squared, the z squared bar cancels with that, right? And then the 2z bar, they combine to give us 4.
Yes.
Z bar, right?
Yes.
And remember, we have a 4 as our denominator. So
yes.
The bottom part has just been simplified to z bar minus z
minus z minus bar and plus 1.
Yeah, and that's what yes. I have as well. Okay. So far, so good, right?
And yes, so far, so good. And in the top, we have z bar minus 1 on the top.
Yeah, so after doing all that, so let's write it. Let's write the result. So we have our function. We just transformed our function. It's now a function of z. The idea was to have only one variable in the function to make our work easy. So this is z minus 1 bar. And then at the top we have z bar.
Z bar minus z.
Minus z. Minus z bar.
Minus z bar.
Plus 1. That's what we have. That is what we have. So we need to do something else. We are almost there. Oh, I see what just happened. We can rearrange it. What are you saying?
We can take z. No,
we can take z out.
Z out, and we'll have z bar minus 1.
Z bar minus 1.
And
then we can take minus 1 out. And we are going to have
yes,
z bar minus 1.
Yes.
And so this is going to be z minus 1.
Minus 1.
Z bar minus 1 over z minus 1.
Z minus 1.
Z bar minus 1. And the 2 cancel out. So our function has been reduced to 1 over
z minus 1.
Minus 1. Right?
Yes.
So I hope you've written all that.
Yes.
So our function f of z is equal to 1 over z minus 1, right?
Yes.
So if it is equal to 1 over z minus 1, and we are checking whether the function is analytic, right?
Yes, for analyticity.
So we can just differentiate it. We can just do a derivative.
Using differentiation rules?
Yep.
Or the first?
So if you do a derivative, what do you get? It's going
when
to
you're
be,
saying derivative, what should I use first? The first principle formula?
so this is, you can use the power rule.
Okay, power rule.
Yeah, because you know this is going to be z minus 1
power rule
to the power of -1, right?
Negative.
So the -1 drops down.
We can just say like that.
And then z minus 1 powered by -2. So
Negative
the derivative is going to be -1 over z minus 1 squared, right?
Yes.
According to the power rule. Okay. So this function, it's going to be analytic. But remember, for an analytic function, it has to exist, right? So we are going to say that this function is analytic everywhere, but there is a point where it's not analytic. So it's analytic everywhere apart from the point z naught equals 1. It's not analytic at the point z naught equals 1. Yeah. And the reason why it's not analytic at the point z naught equals 1, it's because f of 1 is equal to 1 over 1 minus 1, which cannot be defined, right? Because 1 minus 1 is 0. We cannot divide by 0.
Okay.
Yeah.
But complex differentiation, it's also the way how we can find, is this function analytic or not, right? It's everything, the ways to find, is this function analytic or not? I'm repeating myself.
Okay, so how to find whether a function is analytic or not? Remember, we have 2 ways. The first way is to check whether the derivatives of the functions are going to exist. The second way is to check using the Cauchy-Riemann conditions. So you can use this way, or you can use the Cauchy-Riemann conditions.
Could you repeat me one more time? The first way, what was the first way?
The first way, it's the one that we have used. Finding its derivative.
Okay.
Yeah. Finding its derivative and checking whether it's going to exist. Yeah. The second way is,
so I mean, Cauchy-Riemann condition, use Cauchy-Riemann equation.
Yeah.
Cauchy-Riemann equation.
Yeah.
I mean, the main idea of what we're studying here, I mean, instead of SD decomposition, about everything, this complex differentiation, the main idea is to find, is this function analytic or not, right?
Yeah.
To find this, we need to use two methods. First method, it's a derivative, where we can find derivative of our function, or second way, we can use Cauchy-Riemann equation.
Yeah.
For derivative, we can use the first principle formula, or we can use our differentiation rules, right?
Yeah.
Okay, but when we're using derivative, we're trying to find limits or not.
So you only use limits to find a derivative if you are using the first principle. You know, we have many methods of getting derivatives. It's only one of the methods that's going to apply limits. The other ones don't.
Okay, I get it. So we clear with analytic functions, but when we're talking about continuity is different thing than analytic, right?
Yeah.
And continuity we can find also by limit and by function at this point, and there must be equal to be analytic, or to be continuous. To be continuous, yes. Okay. So we have only two aims to find. I mean, continuity and analytic. Is this function continuity or analytic, right?
Yeah.
To find continuity, we understand what we need. To find analytic, we talk to what we need. We need differentiation rule, or Cauchy-Riemann equation. Okay, it looks pretty clear, I guess. But analyticity is something different.
No,
right?
It's not.
Analyticity, where we using when we're finding. Sorry about that. It's
so
everything.
Analyticity, it's the same thing as analytic. So analyticity,
it's the same thing as it.
So analyticity is me and you talking about analytic functions.
Okay.
Yeah.
But we're using two cases. We finding the limits along one axis. I mean, like for example, x-axis, and second, when we're finding limit along another axis, right?
Yeah, we are trying to find the derivative. For example, I believe you're talking about this example, right? You're talking about this example.
Yes, right.
So in this example, we are trying to check if the function z bar is analytic. And we want to check, we want to find out whether this function is going to be differentiable. Remember, an analytic function has to have a derivative.
Okay.
And to find this derivative, we used the first principles. So we brought in the first principles, and then we got this limit, right? And then we checked.
Yes.
If we move along the x, if we move along the y-axis, what are we getting? We are getting -1. We are getting that the derivative of this function, when we move along the y-axis, it's -1. And when we move along the x-axis, we are getting 1. So we are getting two different answers for the derivative. And because we are getting two different answers for the derivative, we conclude that this function is not analytic.
It's not analytic.
Yeah.
Okay.
You remember, this was the introduction. This was just introducing us to analytic functions. So number one, and then for a function to be analytic at a point, it has to exist at that point, and its derivative has to be there.
Okay.
So when we looked at this function, we found that the derivative wasn't there. And so we concluded it's not analytic because f prime of z is inexistent.
Okay.
Yeah.
I got it. So
can we look at this function again?
But another way is the easiest way. Yes.
Actually, I was coming to what you are saying. I just wanted us to look at it again using the other way.
Okay.
So f of z
The way.
equals z bar. We want to find out, is it analytic? We already used this way, the first principles way of getting the derivative, and we found our answer. We found it's not analytic. So let's use the other way, the Cauchy-Riemann conditions. Is it going to satisfy?
Yes, that's what I asked.
Yeah. So f of z, it's going to be equal to x minus iy. Because z bar is x minus i1.
Yeah, it's not analytic. We can see from here because dx over du dx does not equal dv over dy.
So du dx is 1. dv dy is -1. You see, the two, they are not equal.
It's -1.
Yeah,
yes.
It's -1. And did you realize that this was the dv dy? We just got the dv dy, but now we used the first principles. This was nothing but a derivative of the second function with respect to y. Remember, for this one, we were moving along the y-axis, and that is why the change in x was 0.
Okay.
And then for this other one, we were moving along the x-axis, and that is why the change in y was 0. And so this qualifies to be your du dx. So the Cauchy-Riemann equations, they're just quick. They are quick and easy. Okay.
Cool.
Yeah.
I got it. Now I see it. I mean, like, it's not different. It's the same. I mean,
it's the same thing, but we are just looking at different ways of doing it.
Okay, I understand. Whew. Now it's better for me.
Yeah. If it's better for you, it's better for me.
Yeah. I really apologize, Steven, that you're explaining me the same stuff a bunch of times.
No,
sorry
it's okay.
It looks like everything when I work with you, I mean, like when we have a session, everything is understandable, but when I sit and trying to do it by myself, or when I open my notes, everything is ruined. So can we return to the homework?
Okay, which one?
I'm clear with this one. Scroll down just to check is everything. So I need to do this homework again.
Yeah.
Because I need to use differentiation rules to find these ones.
Yeah.
Or can I use Cauchy-Riemann condition?
Yes,
also,
you can.
I can.
You can use Cauchy-Riemann conditions.
I can.
Yeah.
Yeah, it's easier.
Yeah, but you can find a question in your exam forcing you to use the other way. You know, at times when teachers see that the Cauchy-Riemann condition is easier, they force you to use first principles. So you can find a question saying, use the first principles to show that this function is analytic. In that case, you have to use the limits.
Okay, I will do both. I will use when we're talking, when you're saying first principle formula, it also means that I can use these 4 differentiable rules, right?
Yeah. Did I get your question? Can you ask again?
Let me repeat. Okay, you get it. Okay.
Yeah. But,
I'm asking. Give me a second.
But it's rare. It's rare for them to ask you to use first principles. It's going to be a rare question because, for example, you see this was a very easy problem. You see this one? It was so easy, right? And you can see how long the first principles took so long for a very easy problem. So you can only imagine if you use first principles for this one or for number 2, it's not going to be easy. It's going to be so bulky and long. Yeah.
Okay. But my question was that the first principle formula which we're talking about, it's the same rules. It's the same like formulas which we use in differentiation rules, 4 rules, right? I mean, like when they're asking us to use first principle rule, I can use these differentiation rules to find, right?
Yeah. But,
okay.
Yeah.
But let's move on. So we're clear with analyticity. Analyticity is the same thing that Catcher-Rayman condition, not same thing. So can you open the last notes? I mean, like the last lecture notes.
Okay. These ones?
Yes. 3 important properties of analytic function. And can you scroll down to homework? Scroll down to the homework.
There you go.
Yeah, the first example is the same.
Yeah, it's the one we just did.
Yes, and I also did it, by the way, but it said it's analytic. Maybe it was X plus, give me a sec, maybe. No, it was another one, sorry. Let me very quick. Can we look at the task number 3, where z squared plus 2z? I used the Catcher-Rayman condition and it's not analytic. Okay, I have a problem with the second one when we're talking about EZ.
Okay, can you take me through the third one if you did it? Or did you do
the third one? Yeah, sure. I found, so how we know that the z equals x plus iy, I put x plus iy to the formula, to our function, and I've got
it became x plus iy squared.
Yes.
Plus 2
plus
x plus
2z,
iy.
X plus iy. And I've got x squared negative minus y2.
2 iy.
Or okay, 2 iyx.
2 iyx.
Yes. Minus y2. Minus y2.
Okay.
Plus 2x. Plus 2 iy.
plus 2iy.
And for u section, I've got x squared minus y squared plus 2x. It's our u section. And plus I and I, yes. And imagine I.
Mm-hmm. Oh, so the other one was the v.
V, yes, it's just v, it's 2xy plus 2y.
2xy plus
2y, yes.
This is the v.
This is v. And when we're taking du over dx is 2x plus 2, which is not equal dv over, oh no, it's equal to dv over dy, which is 2x plus 2 as well.
2x plus 2, yeah.
Yes. But du over dy, which equals negative 2y, does not equal, no, actually, I forgot. It's supposed to be negative dv over dx. It's negative. It's also negative 2y. It's just 2y.
Negative 2y.
Yeah, it's equal. Sorry, I forgot about this minus.
So that one satisfied the Cauchy-Riemann conditions, and
yes, it satisfied the condition, and the function is analytic.
Yeah, so that one is analytic. Okay, you did another one?
I also did where it was.
So you did that, you did that.
Mm-hmm.
What else?
I did in the second column, first one, where we have, yes, this one.
This one?
Yes, it's not analytic as well.
It's not analytic, okay.
I just started to use, I didn't make any like simplifications.
Let me check my work and compare with what you got.
Mm-hmm.
So that is x over x squared minus iy. That is example number 2.
Oh, yeah. Mm-hmm.
Okay, so what did you get? I cannot see my work, so let's just do it.
Mm-hmm.
So you started by looking for du
over dx.
d over dx, which gave you
1 over 2x.
Like that?
Yes. Is
No,
it correct?
It's not.
No?
Yeah.
I can't use this for, okay. That's why,
Yeah, you must have, remember the rules, differentiation rules?
Yes.
So
I need to use them.
You need to use the products rule. So the products rule says that if you have a function, f of a function that has two functions, let me not use u and v, because you might think about Cauchy-Riemann conditions. So let me think about a function that has two functions, h and g. And these two functions are somehow multiplied together. You see? So this derivative for this function, it means you do the derivative of the first function, multiply by the second function, and then you do the derivative of the second function, you multiply by the first function. That is what the rule says. Okay. So look at this function u, right? It's a combination of two functions, which we could say u equals x multiplied by the function x squared minus y squared powered by -1. You agree?
Yes.
So this is going to be, you could find the derivative of the first function, 1, and then you keep the second function, x squared minus y squared powered by -1.
Okay.
And then you add, keep the first function x, but find the derivative of the second function, right? So the derivative of the second function is going to be -1
times
x squared minus y squared powered by -2 multiplied by 2x. Now there I used the chain rule.
Why you multiply to x?
Because of another rule. You know, this is one rule, we call it the product rule. So there is another rule,
combined product.
We call it a chain. It says that if you have a function of another function, you have a function of another function, and you want to find the derivative of this whole function, okay? You can find the derivative of the first function with respect to the second function multiplied by the derivative of the second function. So that's why I did the derivative of the whole function, okay? I brought down the -1, the -2, but now because inside here I have another function, I found its derivative with respect to x, which gave me 2x, and that's why I multiplied.
Okay, I see.
It's called the chain rule.
I can use everything. I can use derivative, or I can use Cauchy-Riemann equation.
You know, Cauchy-Riemann equations, they are derivatives. You see, we are looking for du dx. That's a derivative we are looking for.
Yes, it's derivative.
So the Cauchy-Riemann conditions are derivatives.
Sometimes I don't need to use derivative. Sometimes I can just put, for example, in the last example, I mean, where f of z equals x squared minus y squared plus I, 3x squared y minus y cube, right?
Yeah.
Let me find it.
Oh, you're talking about this one?
Yes.
This one is easy because these are simple functions. They are not products of functions.
In this case, I don't need to use neither derivative nor.
You just need to use the power rule. Which
is power rule?
The power rule is the one that
says, yes, I remember.
Yeah.
But can I just immediately use Cauchy-Riemann condition, because we have u part and v part.
Yeah.
Yes. Okay. Yeah. But also another way I can, but it's the same, derivative and Cauchy-Riemann condition.
Cauchy-Riemann conditions and derivatives is the same.
Yes, they will be the same. In this case, the function is not analytic.
Which case?
In this case, I mean, like, this function is not analytic.
This one?
Yes, this function. Yes.
Oh, you already worked on it?
Yes, I did it.
What was your du dx?
du over dx equals 2x.
And then you had dv dy?
2x. dv dy, it's 3 negative 3y2, 3x squared.
3x squared minus 3y squared?
Minus 3y squared, yes.
Clearly, that's not analytic.
They're not equal.
Because the two derivatives are not equal.
Yes.
Yeah.
Okay, I'll do it again. About function where z times z bar.
You also did that?
Can we do it also as well?
Yes.
Yes, I did that. But there is no v part.
There is no v part?
Yes.
Oh, yeah, because this is going to be x squared plus y squared. Right?
Yes, right. And there is no solution, or it's not analytic. What should I say? Yes, it's only your part.
So du dx is 2x, right?
It's 2x, right?
And then dv dx is 0.
Du dy, it's 2.
They are not the same.
Yes, dv dx is 0.
That's enough.
Yes.
And do you remember we already saw earlier?
Not allowed.
Remember we saw z bar is not analytic. We saw it last time. We saw it again, that z bar is not analytic.
Yes, again.
Yeah. Whenever you have a z bar in your problem, you can just say it's not analytic because z bar is not analytic. Oh, and by the way,
so I need to do it.
Oh, I thought this was a z bar, x squared minus y squared. No, that's not. Okay, yeah, it's okay. So you have also done that, you've done that.
That's plus.
You've done that and that. Okay, which one did you do? Which one else?
I have problem with the second one, first one.
Okay.
And which you didn't mark actually.
This one, you have problem. This one,
and
this one,
no,
this one.
Not this. Not.
Okay, which one?
Yes,
this one is okay.
But it's all three. I it's difficult to explain. No. I have problem with. Yeah, I think I can do it by myself. 1 over z. Oh, it's 1 over x plus iy. I need to use. Yeah, it's okay. It's okay. Yeah, it's not difficult. It's not difficult. I'm talking about the second one when yes, this one where I put star in front of the first star. I did this problem. Do you remember? You put a mark.
Yeah, we did
that
this.
I did it.
Which one?
Yeah,
this one?
we did this. And yes, I'm okay with this one. So don't spend time on it.
No, this one?
Oh no, yes, we didn't. Yes, no, we didn't.
We didn't finish it. You remember you gave me this answer and I told you no.
Yes. I have problem with this one. Yes. Yeah. Okay, let me try to do this one by myself. I need help with two problems where where we have E. And can I have a minute, please? Very quick.
It's okay.
To use restroom.
All right.
Thanks. Steven, we forgot about your another student, She's not come, right?
Yeah, I know her. She says she will come, but she usually fails to.
Really? Why is she scheduled these classes? I mean, like, why is it taking your time?
I think you know some students they are working. She's a mom. They just have too many things to do. So I just understand them.
No, I understand. Yeah, this is yeah, of course. If she has another issues, yes, of course.
Yeah.
I thought this maybe she just did. Okay, yeah, it's understandable. Of course, everyone has issues, skills, problems, responsibilities.
Yeah.
So let's move on. Yeah. I asked you to help me with the second problem.
Mm-hmm.
1 over.
So let's do it. Let's do the second problem. So you have, so for this problem, I really need you to practice the rules. So before I start looking at the second problem, I want to try and send you YouTube videos. You need to watch a lot of YouTube videos on Calculus 1. Calculus 1. This is a course that is given at the university level, first year university level. So that is where they practice using different rules of differentiation. Okay. So I have prescribed some videos for you. You can look them up on YouTube, and I can also send you some links. I will look at nice videos, and then I can send you links so that you can practice the rules. Okay, so let's do the second one.
Cool, sounds great.
So this is f of z is equal to e to the power of z. I believe you did the first step. You got e to the power of x plus I1.
Yes, right? Yes. Is this what I did?
And also you did this.
And also we can use.
You also did that, right?
Yes, yes.
And then what else did you do? Did you bring in the Euler's formula?
Euler's formula.
Remember?
I thought we need to make a derivative.
Yes, we need to make a derivative.
I think I need to make a derivative. Yes.
Yeah, that's what you need to do. But again, before bringing in a derivative, before the derivative comes up, you need a u of xy, and you need an iv of xy. That is the first step that comes in before you bring in the derivative. You need to separate the real from the imaginary. So at this point, you cannot do the derivative. So you bring in the Euler's formula.
Yes, Euler's formula, which you give me a second. Should be here somewhere here. Yes. Which is ei theta equals cosinus theta plus I times sinus theta. And we're leaving ex the same times ey cosinus y plus I sinus y. Okay.
And then you expand. This is going to be ex cosine of
cosinus
y plus I ex sine of y, right?
Yes, and now we have.
Now you have your u function.
U and v.
Your u function of xy, and you have your v function of xy.
And now we can find du dx, right?
Yeah.
Now we can reuse Riemann Cauchy-Riemann condition.
Yeah. So
it will be it's x.
So du
xe.
dx. Now, the derivative of ex, it's going to remain the same.
Oh,
so
really?
ddx of ex is just ex. So the derivative function, it never changes the ex.
Okay.
So du dx is going to be ex
the same
cosine y,
ex.
right?
Yes, cosine y.
And what is dv dy?
dv dy is,
You have to differentiate sine y.
oh, give me a sec. Yes, it's somewhere. Okay, it will be cosinus z. We were leaving ex the same times cosinus y.
And are they equal?
It equals. They're equal.
So the first condition is satisfied.
Yes. Let's check second one.
So second condition, du dy.
Ex is leaving the same, but cosinus it's changing to the negative sinus y, and negative dv dx equals ex leaving the same, negative ex sinus y. They're equal to.
They're also
and
equal.
the function is analytic.
That function is analytic. Good.
They're also equal.
Yeah.
Okay. Look at this e. It's tricky one. I mean, like, I didn't know that it didn't change.
Again,
Okay.
that is calculus 1.
Function.
I have so many rules. The rules are so many. I can send you a cheat sheet with the so many rules in it about ex and stuff like that. Yeah.
Yes, please. It will be better. So, okay, I will figure out the rest of these problems.
Yeah.
I'll try to do it by myself.
Okay.
And we discussed about SVD. In conclusion, I just want to double check. So we have two problems to identify: is this function continuous or is this function analytic, right? To identify is this function continuous, we need to meet three conditions: when the limits exist, and where the function of z not exist, and this both must be equal, then this function is continuous. Okay, I understand with continuous. What about analytic? We can use our first principle rules. Also, we can use our Cauchy-Riemann equation to find it, and that's it.
Yeah.
If okay, and because my notes is not so like informative.
Come again, please. I lost you for a moment.
Steven? Yeah. I said that I'm okay with everything what we've done, but I have only one question about L'Hopital's rule. L'Hopital's.
Yeah.
One more time, please. One more. The last one. I will promise.
Okay. So L'Hopital's rule is used when we are finding limits.
Ever finding
It is used
okay.
whenever you are finding the limit of a rational function.
Mm-hmm.
So we use, let me write it. We use that rule, L'Hopital's,
Mm-hmm.
when finding or computing limits of a rational function.
Mm-hmm.
And do you know what's a rational function? So a rational function is a function where you have one function on top of another function.
Mm-hmm.
For example,
On bottom.
this one is rational. This one is rational.
Yes.
Right?
Rational.
This one is not rational. The other ones, they are not rational. This one is rational. This one is rational, right? So let's say you want to talk about this rational function, limit x over x squared minus y squared. You see, this is a rational function. Let me not use y squared. Let me use a number like 5. And we want to investigate.
Okay.
We want to investigate the limit of this function as x approaches
square root 5.
Yeah, square root 5. Or maybe we can, let me change this to be 25 and then let x approach 5. Try using L'Hopital's rule.
Oh, okay. It equals 1, right? Limit when z approaches 5, we need to take a derivative of the bottom and the top.
Yeah. So it's going to be limit x approaches 5.
Limit x approach 5. 1 over 2x over 2x. That's it.
Yeah. And then you plug
and
in
we
5.
Put 1 over 10.
That's the limit. So that's how L'Hopital's rule works. Okay.
Okay.
Also, you can apply L'Hopital's rule as many times as you want. Let's say, let's say we have this function. Let's say we have this function x squared.
Sorry, Steven, could you give me a sec? Steven?
Okay. Yeah.
Steven?
Hello?
Sorry about that.
It's okay. It's okay.
Sorry about that. My kids, they're
all right.
Now it's Halloween time. And yes, they have a bunch of questions. Where are they going to trick or treat? Sorry about that.
How many kids do you have?
So 2.
Oh, 2.
Boy and girl.
That's nice.
Yes, full house. But it's difficult to do everything.
Yeah.
I mean, like,
it's not easy.
So,
yeah.
And also it's difficult to live in foreign. We are foreigners here, and everything is expensive here. I mean, United States, it's really expensive.
Yeah, so, I have had stories.
Okay.
So I was giving you an example, x squared, and then you have x cubic minus 125. And I want you to find the limit as x is approaching 5, right? You could do limit x approaching 5, derivative of the top,
2x,
derivative of what you have squared. At the bottom. Oh, that one goes away.
No.
And then you could also do it again. You can do it as many times as you want. 2, 6,
2.
X. And then maybe you could plug in
X.
your 5 there, 2 over 30, 1 over 15, that's your answer. So L'Hopital's rule kind of crashes the function. It reduces it so that your work becomes easier with every step. Yeah.
Okay. Actually, we use this rule everywhere, but I didn't know that we call this rule L'Hopital's rule.
Yeah,
it's the same as derivative. I mean,
yeah,
but we're talking about the rational
functions.
Yes, we're using in rational functions. Okay, I understand. But for example, in here I can also use L'Hopital's rule. No?
Where?
In a first task on a second column on the right side. No, we can't.
You know, we are not looking for the derivative. We are not using L'Hopital's rule to find the derivative.
It's not rational.
We are not using the L'Hopital's rule to find the derivative. We are using it to find the limit as X approaches a certain point. Yeah.
Okay. Okay. It's a big difference. Yes. L'Hopital's rule is using to find limits.
Yeah.
Okay. A derivative we use to find also limits.
We don't use the derivatives to find limits. We use derivatives to find derivatives. So L'Hopital's rule is using derivatives to find limits. Okay. Yeah, but it's not like giving you the derivative of a function. For example, you see, let me try to illustrate. You see the first problem that I gave you, limit as X approaches 5, X over X squared minus 25, right? You did the derivative of the top, you did the derivative of the bottom thing to find this, right? But if I ask you to find the derivative d dx of X over X squared minus 25, you will not do this. You won't do that.
Oh, I will use a formula.
You have to bring in the product and quotient rules to solve that. So that one is asking you for the derivative of the whole function. But now L'Hopital's rule is just using the derivative of the top and the derivative of the bottom to give you the limit. So it's just giving you the limit. Yeah.
Okay, now it's clear.
Yeah.
Much better. So, okay, I think we're okay right now. I am okay. I mean, how do you feel yourself? How are you feeling?
Good. Yeah, I feel good when a student understands.
Are you tired?
No, I'm not tired. I think you are my first student today. I slept for the better part of the day. I rested because I was working so hard yesterday. So I'm good now.
I understand.
Yeah.
I understand. Cool. I'm glad. So let's move on.
Okay.
Right now, I don't have any questions, but also, if you remember, I asked you to send me some. That's it. It's empty. Everything is empty.
Okay. I think I downloaded the whole of it instead of downloading the only part that I wrote. Yeah.
It's okay. No worries. So what should we do next? So and also, Steven, please send me some examples about SVD decomposition, okay? It's enough, like 1 or 2. It will be enough.
I will.
That's it. Thanks.
I will do that. Actually, you can. I like sending these things when the student is online, because when he goes away, I forget. So we can do the sending at the end of the lesson before you go.
Okay.
Yeah.
Okay. I will remind you.
I think that's it about analytic functions. That's it about continuous functions. All you need to do now, realize that the discussion is so easy. Have you realized that the discussion is very easy, but the problems are not? The problems are not at all easy. Yeah. So what you need to do,
I agree,
is practice and go and review calculus 1, how to differentiate, how to use chain rules, product rules, quotient rules, and then you do a lot of practice and you'll be okay. Yep. Okay. So the next thing in my book is harmonic functions. I don't know about the next thing in your book.
So I didn't send you my lecture.
Check. Let me check. I didn't. I haven't.
Oh, okay. Yeah, sure.
Looked them up yet. So let me check what's the next thing. So it's 10A, right?
Yes,
we already did 10B. Let me look at 9B.
No.
Did we do 9B?
10B was on a Thursday.
Okay. So I'm just looking at 9B. I don't know whether we.
Yes. It's 9B. Yeah, I guess we did it or not.
Yeah, we did this.
Complex variable. Okay, we did it. Yes.
Wait. 9B looks like 9A.
But his explanation is really difficult. Yes.
9B looks exactly like 9A.
But he adding like some new stuff.
Okay, let's use like 10 minutes to see what he's doing. Derivative of a function of a complex variable. This is what we did. That's the definition of that derivative.
Yes.
If fz has a derivative at z equals z naught, then the Cauchy-Riemann conditions are satisfied. They have to be satisfied. Yeah. F prime of z naught exists implies Cauchy-Riemann conditions must be satisfied. Cauchy-Riemann conditions are not satisfied means that f prime at z naught does not exist. So if Cauchy-Riemann conditions are satisfied, then f prime of z naught exists. Just repeating the same thing. Converse result, let fz be defined everywhere in a neighborhood. Is this sigma? Yeah, sigma at z equals z naught.
Yes, sigma.
So you rewrite f of z, it becomes two functions, u of xy plus iv of xy. That is the first step that I told you about. So this function is such that, oh, let me just interpret this. You see what he has written as ux? You see this u sub x? This is the partial derivative of u with respect to x. This is another way of writing it, a simpler way of writing it. Yeah, and you're muted.
Sorry.
Yeah.
But yes, I see.
Yeah,
I get it.
So that's a simpler way of writing it. Mu x, instead of writing du dx, this is quite complicated. So that derivative of u with respect to x, derivative of v with respect to x, derivative of u again with respect to y, derivative of v with respect to y, these derivatives, they must exist everywhere in the sigma neighborhood of z naught. So these derivatives, they must be continuous at z equals z naught And then all these derivatives, they must satisfy the Cauchy-Riemann conditions.
For what? For what? Well, what's to solve what? To prove what? Law converse. What's the topic of this?
It's still about analytic functions.
Oh, okay.
Yeah, everything.
Converse result. Okay, just.
Yeah. So this is everything we have talked about. Then f prime of z naught must exist, and fz is differentiable at z naught. Okay, and you know, f naught is differentiable at z naught. Another word, I could write fz is analytic at z naught. The word differentiable and the word analytic, they mean the same thing. So he's just talking about analytic functions, Cauchy-Riemann conditions. Yeah, that's it.
Okay.
And then he gives you an example. The modulus of that squared, it's going to be z bar. Oh, and by the way, just by looking at this function, do you think it's going to be analytic?
No.
No. It's not analytic because z bar is in there and z bar is not analytic. So it's only differentiable at x equals 0 and y equals 0. It's not going to be differentiable at any other function. Okay.
When we're saying differentiable, we mean analytic.
We mean analytic, right? Yeah.
We mean analytic, okay.
But maybe analytic, analytic is quite wider because for analytic, we must have that the function exists. You know, the function could be differentiable and fail to exist. So this is the full definition of an analytic function. So fz is analytic at z equals z naught if f of z naught exists. F prime of z naught also exists, i.e. the function must be differentiable at z equals z naught. And the derivative of z naught exists in some neighborhood of z naught. That is, the derivative is not so far away from the point. Yeah. So
give me a second.
There is a thin line. Okay.
Okay. Got it.
So there is a very thin line between analytic and differentiable. Yeah.
Okay.
Because if the function is differentiable, it's the major condition to check whether it's analytic. Yeah. Because many times the function is going to exist. Many times it's going to exist. So the only condition that we check on many occasions is whether it's differentiable at the point of discussion. Yeah. And then he gave you another example. Yeah, you can obviously do this. You can even, can you just work this out? And then after you work this out, we check whether his work is the same thing as you produce.
F of z equals x cubed plus I1 minus y cubic. Okay.
So my question is, check whether it's analytic.
Okay.
Is it
I will use Cauchy-Riemann condition.
Yeah.
Du over dx equals 3x squared. dv over dy will equal, oh no, I can't.
Why?
No, I can. I can.
Yeah.
3 1 minus y square. They're not equal. It's not analytic.
It's not?
Yes.
So what is du dx?
3x squared.
What is dv dy?
dy. 3 times 1 minus y squared. Square. They're not equal.
Multiplied by -1, right?
Why in this case you need to use the chain rule? Because it's a
because the derivative of this function on the inside with respect to y, this is going to become 0, and then the y is going to become 1, so -1.
Okay, if we're taking derivative of a function, I mean like 1 minus y, it's a function, right?
Yeah.
And when we're taking derivative of a function, we need to use a chain rule,
Yeah.
right?
Yeah.
Okay, it's much clearer. Okay, got it. Yes, I agree.
So
they're not equal.
So this function is not analytic.
Right.
You see, this function appears to be analytic everywhere, and then your teacher says this reasoning is wrong. And which is the right reasoning? The one you found out. It's not analytic.
Okay.
So he got, did he look for his mu x? Mu x equals to vy. So those are the conditions. And then, so he looked for the points where the two functions are going to be analytic. So f of z is actually not analytic anywhere in the z plane. Nice. Okay.
How we can find it?
So
anywhere.
there is something
but it's
else.
Not analytic.
No. There is something else he's doing. There is something else he is doing, which is very nice. So we just found out that dv dy is going to be -3 1 minus y squared, and then we can kick out the -1, right?
Why it's negative?
What? I multiplied by -1.
Why it's -3?
You see, this was a -1
okay.
behind there.
Now I agree. Yes.
Yeah. So
yes.
So I just bring the -1.
Yes, I thought maybe I lost some.
Yeah. So
in the front.
Because du dx is not equal to dv dy, then the function is not analytic everywhere.
Okay.
Now the question is, if it is not analytic,
it's not analytic everywhere.
You know, we are talking about this is the complex plane. So it's not analytic in the entire complex plane, but it could be analytic at some points, right? So to get those points, we equate, you know, it's only at analytic when these two are equal, right? When the two are equal, right?
Yes,
so
of
we
course.
can equate 3x squared to -3 1 minus y squared. So this is going to be x squared equals -1 minus y squared. Realize that it's impossible to solve that equation. We cannot find. Can we?
And we can say that it's not analytic. Say, got it.
You got that?
No, we're talking about that this function is not analytic. Yes,
Yeah.
and we can find that this because our derivative they're not equal, and it can be analytic at some point to solve this equation, which
so
you
you
wrote
solve that
last
equation
one.
to get
It's not.
the point.
There's no like so. Okay, I solve this equation to get a point.
Yeah.
In this case, there is no point, and we can say that this function is not analytic
At
everywhere.
any point.
Okay.
Yeah. So we cannot even find a single point
At
where
any
that
point.
function is analytic. Okay. Yeah.
Okay.
Oh, look at this example. He has the same example as the one that I gave you. Okay. And we found that this one is going to be analytic everywhere. We did it, right? So we checked the Cauchy-Riemann conditions, and we found that f of z is differentiable everywhere. So f of z is an entire function. So entire means that it's going to be analytic at every point inside the domain D. Okay. Not only inside, but also on the domain. Yeah, everywhere. No, yeah, everywhere. So here's an example. Can we check this? Let's check it, and then we can compare our work with his work. So f of z equals e c z, right? Which is the same as e c. We can say that ECX. Which is EC. EC is the same. Multiplied by EX plus IY. Times EX plus IY. Which is EC. EC, EX times IY. It's not correct what you did. We can't split ECZ because it's multiplying its power. Oh, when it's multiplying. Yeah. So EC. But this is correct. X plus. Yes, this is correct. Right? Yes, X plus Y. And we. Yes, this is correct, right? ECX times ECIY. And we can use this French guy formula. Yeah. Euler's formula, you said, right? Yeah. So it will be it will be ECX the same times E times what do we have C in the top? Oh, cosinus CY, yes. Cosinus CY plus I sinus CY. Okay, yes, same. ECX cosinus CY plus I times ECX. Okay. Okay. And now we need to check for analytic. Is this function analytic or not? Yeah. Yeah. So this is the U.
We need to take this is the U, yes, and this is the V.
ECX cos CY is the U, and then V is going to be
GU,
ECX and CY.
ECX times sinus CU.
Yeah.
Yes.
What is du dx?
So du over dx, it's
going to be ECX cosine,
yes,
CY
ECX
multiplied by C.
C.
We are multiplying by C
Oh,
because of the chain.
Now, okay. ECX times cosinus CY, it's the same, and times also the C. C is a derivative of X, right?
The derivative of CX. Yeah.
Yes.
And then dv dy.
And dv dy equals ECX times to sinus CY. It will be C. Cosinus CY times C. Yes, they're equals. They're equal.
Yeah. So the first
function.
condition
Let's
is
check
satisfied.
another one. The second thing.
Yeah.
Du dy equals ECX came the same times cosinus CY is going to minus sinus CY, and dv dx, I mean negative dv dx equals negative ECX times sinus CY times C. It's not equal, right?
It's not equal. You did du dy.
Du dy equals ECX times negative sinus ECX.
Negative sinus CY.
Negative sinus
CY. And then it's going to be a negative C on the outside.
Why we're taking C? Because is it
the derivative of CY?
dy.
The derivative of CY is C. Chain rule.
Okay, yeah. It equals. Then it equals.
So it's going to be analytic.
Yes. It's going to be analytic.
I don't think he solved it, did he? Why did he
No,
use...
he doesn't. He
didn't solve it. Or if he did, he used a completely different approach. Yeah. Okay. Oh, okay. This one he says it's elementary calculus. He's not going to do it. So this is another example, checking whether this function is going to be analytic. So this is what he did. Okay. dfdz, he got that. All right. 3 important results in analytic functions. And there is something else we didn't talk about. You know, we have talked about checking whether a function is analytic. That is checking whether a function is differentiable, right?
Yes.
What do we do when we find out that a function is differentiable? We didn't talk about finding its derivative, because we have found when you use Cauchy-Riemann equations, they tell you that it's possible to get a derivative for this function. Right?
Yes.
Now, we didn't talk about getting the derivative. We didn't talk about that.
Okay.
Yeah, we are going to talk about it as well. So this looks quite f of z, that is also analytic. Okay, so these are some observations. He's calling them three important results on analytic functions. If the derivative of the function is 0 everywhere in R, then that function is going to be a constant in that region. Okay.
If f derivative of z equals 0 everywhere in R. Okay. But
yeah,
did he provide an example?
No.
Okay, ux equals 0, vx equals 0, ux, okay, 0, uy equals minus vx, ui equals 0. When the function is 0, then it's
so
constant.
He's saying when the derivative of this function is 0,
oh yeah,
then that function itself,
prime.
It's going to be some constant. It's going to be a constant function.
Let me make a note about this. So if derivative of 0 equals 0 everywhere in R, then f of z function will be constant.
Yeah.
Constant in R. Okay, got it. It's the first condition. What was the name of these conditions, of these results? Sorry.
This one?
Three important. Yeah, no. Teacher said that 3 important results of analytic functions. Okay.
Yeah, this is the first one. It says that if the derivative is 0, then the function is going to be a constant function.
Okay.
And then the second result, if a function u plus iv is analytic, then its conjugate will also be analytic.
Okay. If, give me a sec, I will just make a note for myself in our case.
Yeah.
Analytic in R and conjugate of this function will be minus also analytic in region. But it's also constant, right?
No, this has nothing to do with constant.
If fz is analytic in R, then fz bar is also conjugate, is also analytic.
Let's say you have fz equals x squared. Let me use I wanted to use, okay. So let me just give an example. So we just checked and we found that the function fz equals e to the power of z. it was analytic, right?
Yes.
That function was analytic. And actually, when we opened it up, it became cosine.
Yes, of z.
Cosine of, actually it became,
no.
When we opened it,
X plus
it became
IY.
EX cosine of Y.
Yes.
Plus
I
EX
cosine
sine of Y, right?
Yes, right.
So if this function is analytic, okay, then this number 2 says that it's conjugate, which is going to be EX cosine of Y minus I EX sine of Y. This is its conjugate. Because the first function is analytic, then the conjugate will also be analytic. There is no need to check whether this second function is analytic.
Okay, I understand. But my question was, in his explanation, he said that fz equals u plus iy is analytic in R. Then conjugate of this function is also analytic in region. Then fz is a constant in the region R. That's what I asked.
Oh. Oh, okay. Yeah, sorry.
No worries, no worries, yeah.
I got it wrong.
Also analytic.
I got it wrong. So let me repeat. I didn't see the last part. So it says that if these two functions are analytic, they can only be analytic if the function is a constant.
Oh.
Yeah.
When they say the function is a constant, what do they mean?
They mean that your function f of z, it's given by a number. It's going to be equal to something like 3 plus 2i. It's not a function with x and y. It's a function with real numbers. That is what they mean with a constant.
Okay.
It's a function that has no variables, x and y.
Okay.
Yeah.
So. Okay, got it. Let's move on.
So number 3 point, let Fz be analytic in R. If its magnitude is a constant everywhere in R, then f of z is a constant everywhere in R.
Let Fz be analytic in R. If its model constant everywhere in R, then Fz is a constant everywhere in R.
Yep.
Okay. Let me write it very quick. Give me a second. R. Then f of z is a constant everywhere. So let fz be analytic in R. Let f of z be analytic in R. Okay, if the model of f is a constant everywhere in R, then f is a constant. How we can check the okay. Did he provide an example of this one?
Yeah,
the third
yeah.
result?
I can see he provided an example. So he's saying, what if you have a function f of z, it's given by the modulus of z. And then he says that, what if it's going to be the constant 0? What if it's going to be the constant 0, right? You know, the modulus of z is simply x squared plus y squared, right? That's the
Yes.
modulus of z. It's going to be 0, right? So if that modulus is 0, you're going to realize that x squared will also be 0 and y squared will also be 0. And so x will be 0 and y will be 0. And so x plus iy will also be 0. And x plus iy is z. So you see, if that modulus is 0, then the function is also going to be the constant 0. You're laughing. Yeah. Did I lose you?
No.
Yeah. Okay. Let's think of another.
No, you didn't. I mean, like sometimes it's okay. I mean, I'm laughing that I think that I'm understanding.
Yeah.
Let's check on. I'm just thinking that I'm understanding. Okay.
Okay. Yeah. So that is a condition that he talks about.
The third result.
The third result. Yeah. Okay. So if c is not equal to 0, f z c squared. F of z is not 0. Anywhere in R, f that. F z is a constant. So he's trying to do the same thing, but now instead of using 0, he's just using c.
Constant.
A certain constant c. So he starts by saying that, let's say the modulus of this function f of z, let's say it's going to be a constant that is not equal to 0. Right? You know, the modulus of a complex function will be the same as its that function multiplied by its conjugate, right? Equals, if that modulus equals c, then these two, they are going to give you c squared. Because you know, the length of f of z is going to be equal to the length of f of z bar. They are going to have the same length.
I didn't get. You said that the module of f of z, it's a multiplication of fz and fz bar, right?
No. The modulus of f of z is its length, right?
Yes.
And
square root of.
Yeah, it's going to be the square root. So f of z is going to have the same length as f of z bar, right?
Oh, yes.
So that is why I'm saying f of z times f of z bar equals c squared, because they have the same length, right?
Yes, I agree.
So this function f of z, it's going to be equal to c squared divided by f of z bar. But this is a length, it's a constant, right?
Yes.
And c squared is also
just
a
will
constant,
be c,
right? So do you see why we are saying that that function is also going to be a constant, right?
Yes.
Which will actually be the c itself. So f of z, if the modulus of the function f of z is a constant, then the function will also be a constant. Yeah. So that's the number 3 results on analytic functions.
A bit on curves in the zip line.
So if you have those two curves, if you have those two real functions of a real variable t, continuous functions, they are continuous inside that interval, then the complex function zt equals the first function plus I multiplied by the second function. If z of t1 is equal to z of t2 and t1 is not equal to t2, then a plus b coincide. Is that what coincide?
I think it's coincides, yes.
Oh, a and b coincide, then the curve is not going to be closed.
A bit occurs in the z-plane in real functions called real variable t.
Oh, yeah, yeah. Do you see that?
Not, I didn't get.
So he's saying that if you have a function z of t1, right? And t1 is so far away from t2.
Okay.
But now the two functions, if they are the same, if this is the same as this, then they are going to be the same point. If they are the same, then they are going to be the same point, right? Let's say A,
yes.
Let's say A is this point and B is also this point. You see what's happening?
It's
the curve
closed.
becomes closed. Yeah. So that is the definition of a closed curve. And there you have a closed curve. So a closed curve that is nowhere
intersects itself is called simple.
Oh, a closed curve that nowhere intersects itself is called simple. So this is simple, right?
Yes.
But this is not simple, right?
Yes.
Because it's intersecting itself somewhere there. So simple, not simple, not a simple closed curve. So R, the region R is called simply connected. If any simple closed curve can be shrunk,
yes,
to a point without
leaving R.
Leaving R.
Shrink, it's mean like making smaller.
Yeah.
Or yeah.
Yeah. So multiply connected region. So that is simply connected region. Multiply connected region. So it's simply connected if any simple closed curve can be shrunk to a point without leaving R. Well, okay, so this one is clear to me.
It's clear to me too, because we can, it means like we can make it smaller without leaving this R z-plane.
How about the multiply connected region?
I think here it means that we have like a few closed curves which are multiply connected, one inside another one. Or they
so
can
for you to shrink a curve to a point, you are going to leave the region. So consider this to be a region. The whole of it is a region, right? And then consider this one to be another region. But now this is the region.
Yes.
Right?
Yes.
So take a simple curve inside this region. You can shrink it to that point and you are not going to leave the region. So this one will be simply connected, right?
Simply connected.
But now take a curve on this other region, right? it's closed, right? And then you shrink it to this point. You see, as you are shrinking it, you get to this part, you have gone outside the region, you have left the region. And yes, so this is going to be multiply connected
regions.
So this one is going to be a multiply connected region. So a curve in Z plane is going to look like that. Sn is that.
Phi, what's the letter is? Epsilon, looks like epsilon. Phi.
What is he trying to say?
Curve in Z plane. N equals f of. He can provide more information in the next lecture. I mean, like sometimes discussing about the previous, maybe if we can find something.
So f of that.
That 1 times delta Z1.
Z1 minus Z0, that's delta Z1. So we
have a curve AB, and we have points such as Z1, Z2 to the Zn on our curve. C is a contour, and that is a middle of our each section. That's what he's trying to say, or not?
Yeah.
Yeah, it looks like function of that 1, Z1 minus Z0. It's delta Z, and f that 2 times Z2 minus Z1 is delta Z2, and so on until the n.
I think he's trying to define the length of a function.
Yes, maybe. Yeah, it looks like.
So he's cutting it into smaller segments and then adding it together. So maybe he's trying to define the arc length. Yeah, this must be the arc length. Oh, and then he brings in integration A to B f of z dz. Oh, okay. I think he was just trying to show us the arc length. So that was 9b.
The same.
Yeah.
What he's talking about in the previous lecture.
So
they're starting integration.
Yeah, he's taking us to integration.
Everything is gonna mix in my head again.
Yeah, I don't intend to go into this now.
Yeah, it's better to. Cauchy-Garcet result. GG result, CG result.
Cauchy. Okay. If f of z is analytic on a simply connected region and C is closed contour in R, then that is going to be 0. Okay. So several things coming in. Okay, interesting. Let me just check my notes to see whether I have that. traversal of a closed path. Cauchy's theorem. I'm just calling it Cauchy's theorem. I see they brought in a word, the name of a person. Cauchy integral formula. Power series, Taylor series. Oh, even these ones are not any simpler. Lorentz series, zeros of a function. All right. Okay, so let us now go back a little bit to analytic functions. And I'm going to open, let me open this. So this one was complex differentiation. And we have this. Let me use the next one. Yeah, this one.
That's it. Everything is empty.
Oh, okay. And let's talk about, we found out that this function.
Which one?
This one. We did a du.
Yes. Yes.
We did a du. We did a du dx on it.
Yes. Du dx it's equals 2x.
2x. And then we did a dv
dy,
which was
3x squared minus 3y2. 3x squared minus 3y2.
So what was the conclusion?
This function is not analytic because the first, like, they're not equal.
It's not entire.
It's not entire.
That is, it's not analytic everywhere. Not analytic everywhere, right?
Yes.
Meaning, if this is the region that we are talking about, it's not going to be analytic at every point inside that region. That is what we conclude.
I agree. Okay.
But it could be analytic at 2, 3, or some few points in there.
Oh, yeah.
Right?
It's getting interesting. Yes.
It could be analytic in there somewhere.
Yes. So to solve
you need to find the 2 points.
Yes. 2x equals 3x squared minus 3y2. Okay, let me find some points.
2 dots x equals
where
x squared minus y. 2 dots x equals x minus y multiplied by x plus y.
Right. 2x equals 3x squared minus 2y squared. Will be 3x equals x squared minus y squared.
One of the points, it could be differentiable at the point 0, 0.
When x equals y.
When x equals 0.
Yes, only when x equals 0.
And also when y equals 0.
When also y is equals 0. Yeah. Yes.
At least we have found one point where the function is analytic.
So this function is analytic, only analytic at point
0,
where,
0.
Yes, 0, 0. When x0 and.
And what does that mean? If it is analytic at that point, it means that we can find its derivative at that point.
Okay.
Right?
Yes.
That is what it means. Okay. Let's I want to pick another function. Yeah, this one. F of z equals z squared plus 2z. Is it analytic? You can just tell me yes or no.
Yes, it's
you already
analytic.
did it. Du dx
Yes.
was 2z.
Du dx is 2x plus 2.
Oh.
Yeah, we change it to x plus iy.
Yeah. Du dx was what?
2x plus 2. 2x plus 2.
2x plus 2. And then dv dy was also 2x plus 2, right?
Yes.
And we found out that it's an entire function. It's analytic everywhere in the domain. Now, can you find its derivative? Can you do a df dz on it? Df dz is going to be the partial derivative of u with respect to x plus the partial derivative of v with respect to x. Because after finding out that the function is analytic, it means you can find its derivative. And now this is how you find its derivative.
Okay.
Yeah. So the other, yeah. So whatever we talked about earlier was checking if the derivative can be found. And then now we are talking about the process of finding that derivative.
Do we need to sum du dx plus dv
dx
or
yeah?
Oh, dx. Okay. So du dx is 2x plus 2 and du dy, dv dx is minus 2y.
So 2x plus 2 minus 2y, right?
Yes, it's our derivative of our function.
Okay. X squared minus 2 iyx minus y squared
plus 2x
plus 2x plus 2y
plus 2 iy
or plus 2 iy. So this is
x squared minus
y squared. That's your
plus
u.
2x. Plus 2x also. You forget 2x.
Plus 2x.
Plus 2x.
And
it's
then
u as well.
The v is negative 2 xy plus 2y, right?
Y negative. It's positive.
It's positive?
Yes.
Yep. So du dx is going to be 2x plus 2.
Plus 2.
And then dv dx is going to be?
It's just negative 2y. Oh, in this case, we don't need to use negative.
Yeah, so it's going to be positive 2y.
Positive y, yeah, sorry, yes.
And so this is going to be?
Positive 2y.
Yeah, so it's going to be 2x
plus 2
minus
plus
2y plus 2, right?
It should be plus 2i, because we don't talk the dv dx. Previously we used negative dv dx. In this case, or it's still negative?
plus, it's going to be plus 2y.
Yes, yes, it's plus, yes.
So this is 2x plus y plus 2.
Yes. Or x plus y plus
and also whenever you're finding the derivative, remember v has an I. The I has to come in. dv dx is going to be 2iy, not 2y. You take your I with you. You know, you're finding the derivative now. Okay. Which is going to be 2x plus iy plus 2, which is the same as 2z plus 2.
Plus
That's
2.
the derivative.
Yeah, it looks like.
Okay.
It was easier to take a derivative of the function.
Yeah, I did this.
Plus 2.
You know why I did this? At times we do things in mathematics to prove that it's true. Okay.
Okay, yes.
So if you take the derivative of the function, you can see it's 2z plus 2. So what does that tell you? It tells you that this is how you find the derivative of a complex valued function. Yeah.
Okay.
So you just take du dx plus dv dx. We call it the total derivative. Yeah.
Cool. Now it's much better.
Yeah. And I think
I now understand it.
So right now, you should be able to find limits. You should be able to check whether a complex valued function is continuous. You should be able to check whether it's analytic, and you should be able to find its derivative. That's it.
Yeah.
Yeah. And then we are ready to look at integration. In some future
tomorrow
lesson. Yeah.
I will. Yeah, I will. I understand that it's better to work in morning, and it's the same time tomorrow, 8 a.m.
You are 8 a.m. Yeah.
Give me a sec. I will check the time.
Okay.
Let's schedule it immediately.
All right.
Update.
I was to give you homework about what? Oh, SVD.
Yes, SVD decomposition. I just can confirm lesson. Yes, of course. 5 stars. Okay, and schedule lesson for tomorrow. Also, I need to schedule 1 hour more, right? Yes.
Yeah.
Okay, I will schedule 1 hour for today. I will just it's always asking me to make it weekly.
And you know, when you make it weekly, students end up losing their money because they don't know they have a lesson at a certain day.
Yes, it's so tomorrow you have a spot at 8 a.m. I will schedule it at 8 a.m. Okay.
Okay. You found a spot there?
What do you say?
Oh, you found I have a spot tomorrow at 8 a.m.
Yes.
Okay. I'm also going to open the other spots for you.
What time?
Yeah. The same time.
I just thinking tomorrow is, what should I do? Tomorrow I have class. I think I have enough time to do everything. Let's make 1 hour for tomorrow, okay?
Yes, and that's okay.
Yeah, we will do more on Tuesday because I need on Mondays I have like appointment with doctor. I mean, not doctor. I need to make a screening test for COVID-19 in the university, and it took time to sometimes it depends on the queue, in the line and how much people there.
Yeah.
But I have to do it. So I scheduled lesson for tomorrow, and also I scheduled another lesson for today, which we are not meet. I'll just confirm it.
Yeah.
So, okay.
That would be great. Yeah, sure.
Yeah. Yeah. Okay. Steven,
All right.
can we finish now?
Yes, we can finish now.
Yeah.
I'm just looking for your singular value decomposition exercise. Yeah, because I have this habit. If I leave the lesson,
of course, it's a good habit.
I just go and sleep, and then I forget. I needed to do something. Yeah, this one is nice. Find the distinct singular values of A. Oh, they just want singular values there. Oh, okay. But it's okay. We can just end here. I will make sure to send you an exercise once I find it.
Thank you.
All right.
I'll appreciate it.
Yeah.
So, Steven, thanks. Have a good night. Have a good rest. See you tomorrow.
Have a good day. See you tomorrow.
Bye.
Bye-bye.